All right, so now a dilution formula. When we work with dilutions, you will see in your text that the formula for dilutions is m sub 1, v sub 1 is equal to m sub 2 times v sub 2. In the dilution formula, m stands for molarity, v stands for volume, subscript 1 stands for first or the initial conditions, 2 stands for last or final conditions. Now, just so you are aware, dilutions do not only work with molarities, but they work with a wide range of concentrations. So very often I like to rewrite this concentration or this dilution formula as C1V1 is equal to C2V2, where C then would stand for concentration, V for volume. Now when you work with the dilution formula, the big key is that you need to keep in mind that the volumes must be in the same units and the concentrations must be in the same units. And if you're using this one over here, this has to be a solution-based concentration. In other words, one where it talks about the mass of solute or amount of solute per amount of solution. Not per amount of solvent, but per amount of solution. So what we're going to do here is we're going to go through some calculations with these, and just to see what your initial sense is before we begin. If it dilutes something, the final concentration of the solution should be, oh come on folks, it should be 100%. Final solution should be less than the initial concentration, because if you dilute something, it is going to be watered down. There's going to be less of it, so concentration has to be less. So that's one of the things that when you do these dilution problems, you need to think about it in terms of your answer. Then if you go to the next one, when a solution is diluted, the volume of the diluted solution is what compared to the volume of the initial solution? This should be 100%, folks.
Yeah.
So we'll get your answers locked in. And we'll count down. 5, 4, 3, 2, 1. Come on. If it dilutes something down, you're starting with a small volume, you wind up with a bigger volume. So think about that. That's what it is. All right? So when you dilute something, again, the concentration becomes smaller, the volume becomes larger. And you got to realize it, because if you don't know that, then when you calculate your answers, you can't even ask yourself if it makes sense. So this is like algebra 0, 0, 0. I mean, this isn't much here. So think about it. Think about it. All right. So what we're going to do then is we are going to look at a few dilutions. And I think before we do that, just point out that I did post the answers to the problem that we did at the very end of the hour on Wednesday. So you should have gotten lead nitrate as the limiting reactant, 3.75 grams of lead 2 chloride as the theoretical yield, and 65% yield for the product. So again, this was posted to the notes for Wednesday. If you have any questions, you can go back and look through it. So today, we're going to work with these formulas, and we're going to start with this very first one. We'd like to know, what is the concentration of a solution prepared by diluting 25.0 milliliters of a 200 part per million mercury 2 solution to volume of 2.00 liters. So for this one, we'll use our dilution formula, C1V1 equals C2V2. What is it we're looking for in this problem?
Concentration of the solution.
All right, and are we looking for the concentration of the solution we're starting with, or the solution that we're ending with?
Ending with.
Ending with. So what I like to do with these is I like to go through and label them before I begin. We are looking for C2. So if this is C2, then this concentration here must be
C1.
C1. Then we have our two volumes right here. We have 25 milliliters and we have 2 liters. So remember, when we dilute, the volumes are getting bigger. So which of these two is the bigger volumes? 2 liters. So this is going to be
V2.
V2. This one here would be V1. So now that you have it set up, I always recommend doing the algebra first and then plugging in the numbers last. So we are solving for C2. If we solve this one for C2, we divide each side by V2. V2 cancels out, and it tells us that C2 is going to be equal to C1 times V1 all over V2. Now, of course, we take a look at this. We see that one volume is in liters, one volume is in milliliters. So if we're going to calculate this, we need to make sure that both the volumes are in the same units. They can't be different. They won't cancel out. So it doesn't really matter which one we convert. I like bigger numbers rather than smaller numbers, so I'm going to convert liters to milliliters. If we take the 2.00 liters, convert this over to milliliters, what is the relationship between milliliters and liters?
1 liter.
1 liter. Okay, where does the 1 liter go? On the bottom. On the top we put in 1,000 milliliters. The liters here cancel out. We take 2 times 1,000. We wind up with an answer of 2,000. Of course, that's still going to have 3 significant figures. As long as we remember that, we're cool. So C1 then is 200 parts per million. So it's 200 ppm of the mercury 2. We'll multiply that by V1, which we said was 25.0 milliliters. We divide this all by the 2,000 milliliters. Of course, that's with 3 significant figures. We go ahead and calculate this out. 200 times 25. We divide that by 2,000. And we wind up with an answer here of 2.5. How many significant figures should be in that answer?
3.
So we'd write it as 2.50. The label would be parts per million of the mercury 2 ion or the concentration. So once you get it, we should then ask ourselves if it makes sense. Remember, when we dilute something, what happens to the concentration? It should go down. And did the concentration go down? It did. We're good. Now, another key piece, if you have any trouble with these whatsoever, we have 2 quantities here separated by the word of. Whenever we have 2 quantities separated by the word of, that means we're doing what operation? Multiplication. And did we multiply those 2 values together?
Yes.
We did. So on several accounts then, this answer should be one that makes sense. Any questions? All right, let's do the next one. We'd like to know what volume of 2.00 molar sodium carbonate is needed to prepare 3.00 liters of a 0.100 molar sodium carbonate solution. Now, it doesn't say this in the problem, but when you calculate this, you should put it in the units that make most sense. In other words, what you're going to use as a measuring device in the laboratory. So we might answer it in liters, we might answer it in milliliters. Probably easiest though to begin calculating with liters and then seeing if it's one that the units make sense. So our formula here is going to be M1V1 is equal to M2V2. What are we looking for in this problem? We're looking for a V. So are we looking for the starting volume or the ending volume? Starting volume. Because if we're preparing 3.00 liters, That must be the final volume over here. So we must be looking for the initial volume. And then we look at the 2.00 molar, the 0.100 molar. Which one is the, let's see, M1? Is this one M1 or is this M2? M1. And then if this is M1, that must mean that this concentration here is M2. And again, you go back to the questions we asked when we started here today. When you dilute something down, the concentration will go down. So that's how, even before you begin, you can ask if it makes sense. Again, my recommendation is always to do the algebra first, then plug in the numbers. So we're trying to find what V1 is equal to. We want to find what V1 is equal to. We divide each side by M1. M1 cancels out. Not M1. Yeah, M1 cancels out. I don't know why it cancels out V1. That's kind of stupid. How about that there? There we go. So V1 is equal to M2 times V2 all over M1. We go ahead and plug in the numbers. M2 is 0.100 molar sodium carbonate. We have a volume of 3.00 liters. We divide this all by the 2.00 molar sodium carbonate. And what happens to units? Molarity will cancel out. So then if we calculate a solution for this, we would take 0.1, multiply it by 3, and divide it by 2. When we do that, we wind up with an answer of 0.15. How many significant figures should this answer have? 3. And the label on this would be liters. Now chances are if I sent you to the laboratory, you're not going to go out and well, you will measure 0.150 liters, but you won't be measuring it in those units. What units would you be using?
Milliliters.
Milliliters. So again, put it in the units that make the most sense, something you'd actually measure the units in. So if we want to convert this to milliliters, we take 0.150 liters. We'd convert it over to milliliters by using our conversion. On the bottom we'd put in
1 liter.
And on the top
1,000 milliliters.
1,000 milliliters. Liters cancel out, and that of course will give us an answer of 150 milliliters. Put the decimal point at the end there to indicate that the trailing zero is a significant figure. Once we get the answer, we should ask ourselves if it makes sense on a couple of counts. Initial volume, should it be smaller or larger than the final volume? Should be smaller. Is this smaller? It is, so it makes sense. On a second account, we have two quantities separated by the word of, and that means we take those quantities and multiply. And did we multiply them together?
Yes.
We did. So on a couple of accounts, then it makes sense. There we have the answer. Any questions on this one? We could just do dilutions all day. We'd like easy stuff like that, right? Okay, then, if we go to the next one here, we'd say, assuming the volumes are additive, what volume of water is needed to prepare this solution? So how do you think we go about finding the amount of water needed? Any ideas?
Would you just take 3 liters and subtract 150 milliliters?
Yeah, we're going to take our 3 liters and subtract 150 milliliters. Of course then, and I know you already knew this, we need to make sure that we are in the same units. So it doesn't really matter which units. Oh, it does, I guess. So we want this in milliliters. So if we want this in milliliters, we had changed the 3 liters to milliliters, which would be 3,000 milliliters. And we'll go ahead and subtract. And I think this was 3.00, right? So this is the uncertain digit here. So we take and subtract, we wind up with 2,850 milliliters. Of course then, because the uncertain digit was this one here, that means that this place is uncertain. And usually we don't write it with a digit underline. Rather, we would convert this to? Not to liters. Well, we could, except it specified milliliters. Put it in scientific notation. So putting in scientific notation, I write it as 2.85 times 10 to the third. The label would be milliliters. And of course, then these two quantities, this amount of water and this amount of the solution, should sum to be 3,000 milliliters. When doing your dilutions, I brought out a variety of glassware here today. We should be aware of what all of these pieces of glassware are. We did talk about these already. These here are called a volumetric flask. So these are volumetric flasks. They do come in, as I mentioned the other day, I didn't have them out, they come in a variety of sizes. This is not the smallest we have. We actually have, I think, a 5 or 10 milliliter volumetric flask. This is not the largest we have. This is a 1 liter. We have, I believe, a 4 liter volumetric flask. So they range in all sorts of sizes. They do measure just one volume. That volume is a scratch or line that goes around the neck here. So if we would prepare a solution like this, one of the ways we could do it is to add 150 milliliters of solution. Some devices we could wind up using to do that. We could use these, which are called pipettes. If you don't know how to spell them, they're actually spelled two different ways. One way is P-I-P-E-T. The other way is P-I-P-E-T-T-E. I don't know, it's like they feminize it or something. So pipette, they're both the same thing. Sometimes you have graduated pipettes like this. This type of pipette is called a Mohr pipette. And that's not M-O-R-E, but it's M-O-H-R with a capital M, named after, I suppose, a person who first created it, just like we refer to them as Erlenmeyer flasks or Bunsen burners. This here's a Mohr pipette. This type of pipette is called a volumetric pipette. And so volumetric pipettes, volumetric flasks, we use that term volumetric, that means that they are going to measure just one volume. But they measure that one volume very precisely. In the case of a volumetric pipette, part of the design on it is we have a very thin top. Likewise, on a volumetric flask, we have a thin top, and that helps determine that precision and accuracy of those measurements with these devices. And the way that these are made out in the factory, there's actually somebody whose job is to sit there and fill these things up with water, and they'll measure the temperature of the water, and then they'll fill it up to, like in this case, probably like 1 kilogram of water, and then their job is basically to etch that line in around there. So it is something that is, if you were to break one of these here are not cheap, because again, it is a labor-intensive task not only to make it, but there is one person's job to go ahead and fill these up very precisely to measure those volumes. Okay, now we could go ahead and use these devices if we don't need quite the level of precision or accuracy. These devices are called graduated cylinders. And of course, if we want the least precision, we'd use these, which are called beakers. And I don't have an Erlenmeyer flask out there, but many times when you go in the lab, well, I know it'll say this right on here. This one says these are approximate volumes. So if you're going ahead in the lab and using these to measure volumes, you are not doing so accurately, because even on the device itself, it will say that these are approximate volumes. Sometimes it'll say plus or minus 5% or plus or minus 10% on there. So these here are relatively inexpensive because we haven't taken a whole lot of time to determine the accuracy or precision of these. Okay, any questions on the glassware devices? And since I'm not teaching lab this semester, have you used the volumetric flask yet? Have you used pipettes yet? Yes. How about more pipettes? Yes? No? No? Okay. But I know for sure, I mean, it wouldn't be a chemistry lab if you didn't use these already. So, Okay, well, we're going to set this aside, and we're going to get into something new and different. And I think the rest of the stuff from here and out to the exam, I could be wrong, there's no calculations involved. Well, there will be some when we get to oxidation numbers, but that's going to be simple integer algebra, addition and subtraction. So that'll be single digit, and we can all do single digit stuff in our heads, I hope. Okay, so what we're going to do though is we're going to start by using this device, and this was the device I got mixed up with. I thought that I had shown this in your class, and I don't think I have yet, have I? No? Okay, and so what this device is, we've plugged it in. It's a very old device. They wouldn't sell one like this today because it's kind of dangerous. We just don't want to touch the tips. But if we go ahead and complete the circuit here with this piece of metal, we see that the light bulb goes on. So what I'm going to do next here is I'm going to go ahead and take some water, and we want to check to see whether or not this water conducts electricity. And it just so happens I want to see what you know. If I take some water, and we want to check to see if it conducts electricity. Will it conduct electricity? Yes or no? Now you guys get a little leeway on this one because this is maybe not so much common sense. But you might think it is. So we'll count down here. 5, 4, 3, 2, 1. And I did not put the right answer down on this one because we're actually going to demo this one to see for sure. We need like a drum roll. It's too damn quiet in here. There we go. Wonderful. And we see that it does not conduct electricity. So the majority of the class was incorrect, but you get a pass on that. You won't get a pass on the exam. Make sure you know now. Pure water does not conduct electricity. So now, why is it that you think that most people put down, don't be embarrassed because you were with the majority, why do most people think that water does conduct electricity? Yeah.
It's usually ionized, isn't it?
It's usually ionized, yeah. And so if we go back here and dump this water out now, which was the pure water, and I go ahead and take a small amount of this water here, we actually see that with a small amount of water here that does have the ions in it, it does in fact conduct electricity. So what we're going to do then is we are going to take a couple substances, and we're going to start with these two here. We're going to start with some sugar and some salt. And I suppose I should have my eye protection on here now. I'm going to go ahead and put pure water in all of these beakers that I use here today. And we're going to test another number of substances. So what I would suggest that you do is probably get a clear page ready, and we're going to make a table. And in that table, we are going to list, let's see, how did I put this? We're going to put the substance, so let's say they'll put the name of the substance. Well, I'll just say substance. And then we're going to ask ourselves whether or not this substance conducts electricity or not. And the first substance we're going to test is going to be C12H22O11. Anybody know what C12H22O11 is? Sucrose. Sucrose, right. And then we're going to test this substance, which is table salt. So these two here. And let's see, do I have my 2 beakers of water? I do. And I need some spatulas to measure these out. And now what I'm going to do then is I'm going to dissolve these into the water. Sugar is going to be on your left. Get a little more in. Come on. I'm getting a whole bunch. Here we go. That's a good bunch. And then I'm going to put some salt in this one here. And I'm going to go ahead and mix these up. We'll make sure we get some to dissolve. And I'll do the same thing over here. Mix them up, get it to dissolve. And then what I'm going to do here is I'm going to ask you, again, this is a prediction. If we don't get it right, that's okay. This is what we're learning about today. So which substance, when dissolved in water, do you think will cause the water to conduct electricity? Do you think it will be the sucrose, the table salt, both of them, neither of them, or just admit you really have no idea? So get your answers locked in. And we'll count down. 5, 4, 3, 2, 1. Looks like the majority think that sodium chloride will. Many think the sucrose will. Some think both of them. Some think neither. So let's go ahead and check them out. We'll start with the sucrose. All right. Again, we need a drum roll. It's too quiet in here. How disappointing is that? And try out the salt here. Check it out. Ready? Go. And we see that the salt here is an electrolyte. And it goes back to what you mentioned already here, Max. What's in the solution?
An ion, sodium.
All right, that's ions that are present in the solution. So, again, talked about this water being ionized. This water that we take out of the gray taps in lab is said to be deionized. So we take the ions out, and so it's actually ions in solution that make it conduct electricity. And anybody know the name that we give to substances that conduct electricity? Electrolytes, yes. So I think what we'll do is we'll label this column as electrolyte or non-electrolyte. And here's how we define electrolyte. You probably want to write this down. We define electrolyte as a substance that conducts electricity when dissolved in water. An electrolyte is a substance that conducts electricity when dissolved in water. Substance that conducts electricity when dissolved in water. And where have you heard of electrolytes before? Gatorade. And who is Gatorade marketed to? Athletes. And why would athletes need electrolytes? Yeah, why do we need something to conduct electricity?
Charge us up.
Yeah, charge us up. But why do we need it? Why do we need things in our body that conduct electricity? Not energy. It's a good thought, but not for energy.
Something with hydration?
Excuse me?
Is it something with hydration?
It does involve hydration, yes. But if we wanted to figure out, I've had this done maybe once in my life, but if we want to figure out if something's wrong with my heart, what do I have done with my body? They take a electrocardiogram, right? And so basically it's a picture of how the electricity is being conducted through my body, and it shows then the action of the heart as it contracts, and that contraction of your heart depends upon the electrical signals. If somebody has a heart attack and they go through a what is it? Fibrillation? Okay, and then we want to jumpstart their heart again. What do?
Shock it.
You shock it. Okay, and so that's because we need to get those electrical signals going. All your thoughts that you're making right now, you're thinking this is really kind of sappy, right? Those thoughts and your muscle contractions, those all depend upon electrical signals. So nerve impulses, those are electrical signals. And in the case of athletes, it's marketed to athletes because what happens when you exercise?
You sweat.
What do you do?
You hurt.
You hurt, sure. But what happens?
Sweat.
You sweat. And if you ever taste your sweat, how does your sweat taste?
Salty.
Salty, exactly. So the electrolytes then are taken. Basically, when you take the electrolyte, you're basically just drinking salt water. Of course, if you drink salt water, it's not going to taste very good, so what do you do to it? You flavor it and you add sugar to it. But the sugar is not an electrolyte, that just basically provides flavor, and this provides the energy. So the energy comes from the sugar, the conduction of electricity comes from the salt. So that's where the two pieces come from. So if we come back here and label these, we'd say that the sucrose is a non-electrolyte, and we'd say that the sodium chloride is an electrolyte. And in order for it to be an electrolyte, not only does it have to conduct water, but conduct electricity when dissolved in water, it also has to contain ions. So a solution cannot conduct electricity unless it contains ions. So what that means then is we're going to look at another set of substances, and these are going to be the next, what is this? 8 substances that we're going to test here today. So go through these, and you can select as many as you wish. So you don't have to just select one. If you think that 5 of them are electrolytes, select all the ones that you think would be electrolytes. And then while you have it open, you can go ahead and write them down on your notebook, because we are going to test them in this order. So we have KNO3. We have CuSO4. We've got, what the heck was that? I still don't have this whole tablet PC thing down, this new one. Okay, we've got C2H5OH. We've got CaCO3. We've got NH3. We've got HCl. And we have NaOH. And we want to see whether or not these substances are electrolytes or not. Okay, so we come back here. Let's see how we did here. Let's get your answers locked in on these. Again, these are just predictions. They're not going to be marked right or wrong, but just see how well you think you may have done. So we'll count down here. 5, 4, 3, 2, 1. Okay, it looks like we've got high up on the list is sodium hydroxide. Looks like HCl and calcium carbonate. And these two. So let's see, it looks like A, B, and H. Probably D and G. This one's kind of confident for the class. So let's go ahead and check these out and see how we did with them. And I'm going to start here with potassium nitrate. So then on each one of these, I'm going to go ahead and make sure that I use the deionized water. Clean off the spatula. We'll make sure, of course, the water by itself does not conduct. And it doesn't. We'll add some of the potassium nitrate to this. And we'll go ahead and mix it up. And see what happens here. And we see that the potassium nitrate is, in fact, an electrolyte. So again, potassium nitrate, yes, is an electrolyte. And why would we expect potassium nitrate to be an electrolyte? It's an ionic compound. So we will try the next one, the copper 2 sulfate. Again, we'll go ahead and take some water. We will test the water by itself to make sure that the water by itself does not conduct. We'll then go ahead and take some of the copper 2 sulfate. And we have this in its hydrated form because the hydrated form dissolves a little bit more easily than the anhydrous form. mix this one up here. Now, what type of compound is copper 2 sulfate? Ionic. So if it's ionic, we should expect what? We should expect it to conduct. And we do, and we see that it is an electrolyte. So far, so good. Electrolyte. Next up, we have C2H5OH. The name of this substance is ethanol. This here is ethanol. And where do we find ethanol? Alcohol. Right, alcoholic beverages. Where else do we find it? In the state of Minnesota.
Fuel.
Fuel, exactly. It's used as an additive to gasoline. So we'll go ahead and check to make sure that our water doesn't conduct. And it isn't. We go ahead and add some ethanol to this. And we check to see whether this conducts, and we see that it does not. So this would be a non-electrolyte. And as a non-electrolyte, why should we have predicted that this one is a non-electrolyte? What type? It's a molecular compound. Yeah, it's a molecular compound. And so we would anticipate that molecular compounds would be non-electrolytes. It does not make ions. So a couple things here. First of all, don't go drinking ethanol thinking that's will replenish your electrolytes. It won't. Okay? So remember, salt will. The other thing is, don't even think about drinking this in the lab. I know it might be fun to drink ethanol, because that is the consumable one, but anybody know why we shouldn't drink this in the lab?
Concentration.
Not the concentration. Turns out that in the lab we put out,
So no food and drink is allowed in the lab?
well, that's in part, but even still, I've known a lot of sneaky students over the years who would love to take a sip of this. It wouldn't be a wise idea. It's because in the lab we put out denatured ethanol. And when we say that something is denatured, that means we make it unfit for human consumption. And when we denature it, we can actually get it a lot cheaper. If this was pure ethanol, then we would have to pay real high taxes in it. If you would buy something like this in a liquor store, this size, I mean, I don't buy liquor like this, but I'm guessing that this is probably going to be about $20, $15 if it's like pure ethanol, Everclear type thing. And I don't buy that type of stuff, so I don't know. But if it's denatured, we can get the same thing. This is probably about maybe 25, 30 cents worth of ethanol right here. So there's a huge difference in price when you buy it as to consume. It's one of those sin taxes. We have it very highly taxed. But when we use it like denatured or put it in ethanol or in gasoline, of course it's not fit to consume in gasoline either. So it's a heck of a lot cheaper in that form. And now what they used to denature it with was methanol, but it turns out when they denatured with methanol, methanol actually causes you to go blind if you consume enough, so that was not a very wise thing. So today they add a substitute that if you consume it, it actually gives you very severe stomach pains and diarrhea. So don't consume it. That's my tip for the day. Okay, then we come over here. Next we have the calcium carbonate. Calcium carbonate, a common name for calcium carbonate is chalk. Anybody know where else we can find calcium carbonate?
Tums.
Tums, exactly. And if you ever thought that Tums have a chalky taste, you're right, because Tums and chalk have the same substance in them, as does eggshells. Okay, so eggshells, primary component is calcium carbonate. So if you are out of Tums and out of chalk, and you have an upset stomach, you can always chew up some eggshells. That'll do the same thing for you. Okay. Now, what's one thing we're noticing about the chalk here right away?
Not really dissolving.
It's not really dissolving. Exactly. Not really dissolving. And so I could sit here and stir and stir and stir for hours, and if I go ahead and test it, we'll see that it does not conduct electricity. Now we may have predicted that this would have been electrolyte because it's what type of compound? It's ionic. But remember, if it's electrolyte, it must also dissolve in water. And if it doesn't dissolve in water, it cannot be an electrolyte. Okay, so we're going to say that this one here is a non-electrolyte, not because it's a molecular compound, but because it is insoluble. The solid is insoluble. Then we'll check ammonia. Actually, I'm going to skip down. I'm going to skip down to which one? I'm going to skip down to... Did I forget to put it on the list? I think I did. What was the next one on the list? There we go. I'm missing the acetic acid. So I'm going to come back here and I want to do the acetic acid next. So I'm trying to remember how this new pen works. Here we go. We'll scroll that down there. There we go. And we're going to put in HC2, H3O2. And this is the stuff some of you were mentioning you were smelling when you came in today. If I walk around with acetic acid, anybody know? It's vinegar, exactly. So this stuff here is 100% acetic acid. So this here is pure acetic acid. Oh, yeah. Got a good hit off of that one. Okay. Now what I'm going to do here is I'm going to put the acetic acid into here. And then we'll close that up. And then we'll take some water. And we are going to test them separately. This here's the acetic acid. We see acetic acid by itself does not conduct. We take some water. We see by itself it does not conduct. We pour the acetic acid into the water. And we see that this one here does conduct. But now if we look at the brightness of the bulb, how does this brightness compare to the ones we looked at previously? Yeah. Great. That was a good whiff. I got a cold today, so that actually helps. Wow. Okay, so this was definitely dimmer. And if it is less conducting, we actually say that it is a weak electrolyte. And I just still cannot figure the screen out. There we go, weak electrolyte. Which means all of the previous electrolytes we looked at would be classified as strong electrolytes. So we can go back and label these previous electrolytes as strong electrolytes. Then if we look at ammonia, ammonia has a formula of NH3. NH3. And I need to delete this down or I'm going to get myself and somebody else not feeling well. So here's our water by itself. I'll go ahead and dump in a little bit of NH3. And this is ammonia that's already been dissolved in water. We'll check it out. And this one would be classified as a weak electrolyte as well. Now, what would be surprising about ammonia being an electrolyte?
It's a molecular compound.
It's a molecular compound. And actually, acetic acid is also a molecular compound. So we here have two molecular compounds that conduct electricity. In order to conduct electricity, they have to have ions present in solution. But now we don't have time to talk about that today, so that's going to be a first thing on, let's see, next Wednesday type of thing. But we have a couple left here. We have HCl, and so we'll go ahead and take some water here, and we'll make sure that the water by itself does not conduct. And we'll get the hydrofluoric acid and add this to there. And we'll see that the hydrofluoric acid, strong electrolyte, and if we go down to the last one here, sodium hydroxide, we have right here, and we'll go ahead and test the water by itself. We'll go ahead and add a small amount of the sodium hydroxide. And once we add the NaOH, get this to dissolve, we see that the sodium hydroxide is a strong electrolyte. Of course, we'd predict the last one to be a strong electrolyte. Why? Ionic compound, and that ionic compound must be soluble. And so as a soluble ionic compound, we would expect to see that it is a strong electrolyte. Now, as far as these other ones that are molecular compounds, right here, these here are all molecular. And let's put this in a different color here. These here are all molecular. But even though they are molecular, they still conducted electricity. And the reason for that is because these three undergo reactions with water to make ions. So even though they are molecular to begin with, a solution cannot conduct electricity unless ions are present. And so if it is a molecular compound, what that means is it has to react with water to make ions. And if we look at the names of them, let's again remind ourselves what the names of these two are. The name of this one here is acetic acid. This one here we dissolved in the water, so this is, what is the name of this one? Hydrochloric acid. So we have acetic acid, hydrochloric acid. So notice they are both classified as acids. And so it turns out that all acids that are soluble in water are classified as electrolytes. Some of them are strong electrolytes, some of them are weak electrolytes. And it turns out, I will asterisk these in blue, these here are classified as bases. So the ammonia and the sodium hydroxide are both classified as bases. And so this base here, even though it's molecular, is a weak electrolyte. And so here's the thought we're going to end with here today. The thought is this. You've probably heard the terms strong acid, weak acid, strong base and weak base before. Here's where those terms come from. If we have an acid that is a strong electrolyte, we call that a strong acid. If we have an acid that is a weak electrolyte, we call it a weak acid. If we have a base that's a strong electrolyte, we call it a strong base. And if we have a base that's a weak electrolyte, we call it a weak base. So going off of that then, the acetic acid would be a
Weak acid.
weak acid. The ammonia would be a
Weak base.
weak base. The hydrochloric acid would be a strong acid. And the sodium hydroxide is going to be a strong base. Now, because we don't have classes on Monday or Tuesday next week, I know you don't want to have any additional homework or things to memorize. So when you come in here next week, we'll talk about the things you need to memorize. There's going to be a list of strong acids, weak acids, strong bases, weak bases you need to memorize. But no classes Monday or Tuesday next week. That's it. Thank you.